your mic.
Good evening, ladies and gentlemen. It falls on me as the chair of the European Space Weather Programme Committee to to hand over this session. But first, just to say that the European Space Weather Space Climate Medals have been a part of European Space Weather Week since 2013. And I will now hand over to Andrea Optitz, who is the chair of the E-SWAN Medal Committee, to oversee the proceedings for this year's medal ceremony. Andrea.
Thank you. So, ladies and gentlemen, welcome at the medal ceremony and talk tonight. This is for 2025. So, as Pierre said, my name is Andrea Opitz. I'm the chair of the E-SWAN Awards Committee. Since 2013, there are 3 medals awarded, the Christian Birka and Baron Marsa-Nicolai and Alexander Chizhevsky. This is normally yearly awarded by the awards committee, or actually in 2023, the E-SWAN took over the role of the host of these medals. And in 2024, the awards committee of E-SWAN was created. So now the awards are under the sole responsibility of this awards committee. So what kind of awards we have, and also the decision of the procedure. And as well, you will see in the constitution of this awards committee, it's changing from year to year, so even the process might change, and also the awards might change from year to year. So the composition of the E-SWAN Awards Committee in 2025 is from 9 previous winners, from 3 ex officio members, 1 representative of the E-SWAN Executive Board, another representative from the Space Weather Week 2025 Program Committee, and then a representative of the E-SWAN Publication Committee. So these are the voting members, and there is 1 non-voting member. This is myself, the chair of the committee. As I said, we make a call for nominations for 3 medals every year, but the committee has the right to decide not to give an award, not to give any of them, or only 1 or 2. It's changing from year to year. There might be different reasons. We had an unfortunate year when it was a political reason. It can be technical reason, or there were no good nominations. It's not necessarily the person who is nominated, but probably the nomination itself, or just none of the nomination was so convincing, whatever. So this year we will award only 1 medal. This is the Chizhevsky medal. And to introduce the medal and to announce the winner, I call to the stage Ronald van der Linden, the representative of the E-SWAN Executive Board in the Awards Committee.
The Alexander Chizhevsky Medal is awarded to an early career scientist in recognition of outstanding achievements with an innovative approach in the field of space weather and space climate. The nominee must be an early career scientist within 8 years of receiving his or her Ph.D. at the time of nomination. This period may be increased for career breaks. Before I announce who will be awarded this year's Chizhevsky Medal, I'd like to mention that we had many nominations this year most of which were of a particularly high quality. And even if many nominations means a lot of work for the committee to review these nominations, to discuss them and to decide upon it, it still makes me happy to see enthusiasm for these awards. So please keep the nominations coming for the next years and give us even more work. I now call Stefan Putz, President of E-SWAN, to hand over the medal, and Piers Jiggins, Chair of the Program Committee of European Space Weather Week, to hand over the certificate. In 2025, the Alexander Chizhevsky Medal for Space Weather and Space Climate goes to Erika Palmerio. Because I put your photograph up there as well. The Chizhevsky Medal is awarded to an early career scientist, as I just mentioned, whose achievements in space weather and space climate stand out for both innovative approach and lasting impact. Today, by honoring Dr. Erika Palmerio with this medal, we acknowledge that she has more than fulfilled, indeed exceeded, the criteria of excellence, originality, and influence. Erika Palmerio is an outstanding early career scientist whose work uniquely links solar eruptions, interplanetary propagation, and planetary impacts. Her innovative studies on stealth CMEs and complex CME interactions have substantially advanced our understanding of space weather drivers. Her international standing is evidenced by numerous invited talks and the AGU Early Career Award that was awarded to her in 2024. Dr. Erika Palmerio earned her Ph.D. in physics in October 2019 from the University of Helsinki under the mentorship of Professor Emilia Kilpua, a thesis that garnered both the Outstanding Thesis Award of her school and the University-wide Dissertation Award. Following her doctoral work, she was selected for a NASA LWS Jack Eddy Postdoctoral Fellowship, which took her to the University of California, Berkeley, and soon thereafter, she joined Predictive Science Incorporated in San Diego as a research scientist. Dr. Palmerio's scientific oeuvre spans both interdisciplinarity and holistic systems thinking. She has merged remote sensing and in-situ spacecraft observation and coupled those with state-of-the-art magnetohydrodynamic models to illuminate how coronal mass ejections and solar energetic particle events evolve, not just near Earth, but across the whole solar system. Her insights into the intrinsic magnetic structure of CMEs, including the class of elusive stealth CME events, and her analysis of interacting CMEs under complex solar conditions have redefined what is possible in our field. Her work tracking these phenomena across interplanetary space shows not only technical mastery, but the depth of vision to see the heliosphere as a unified dynamic system. Particularly striking is her recent collaboration leveraging the proximity of Parker's Solar Probe and Bepi Colombo near Mercury's orbit to unveil the mesoscale structure of CME ejecta, a study that drew attention in Nature Astronomy and was profiled in AAS Nova. Her publication record speaks volumes. About 70 peer-reviewed papers, 14 as first co-author, a body of work whose quality and impact are unquestioned. The influence of her work is demonstrated through the more than 2,000 citations and in the many invited talks she has delivered across the globe. But Dr. Palmerio's contribution extends beyond her own research. She is already a leader in our scientific community, guiding projects and teams, convening critical sessions and shaping the future trajectory of heliophysics. She serves as principal investigator on NASA and NSF grants, co-leads an ISI international team on tomographic inversion of synthetic white light images, and has played key roles in the structuring of CME geometric reconstruction and stealth CME analysis. She has convened solar terrestrial sessions at EGU annually since 2018, chaired symposiums, served on the steering committee of the Eddy Cross-Disciplinary Symposium, and sat on numerous advisory bodies and review panels. Besides all of that, and as most of you know from the previous editions of the European Space Weather Week, Erika is also a great writer of songs about heliophysics.
I'm so proud of you, yes.
For all of these reasons, the E-SWAN Awards Committee has decided unanimously to attribute the 2025 Alexander Chizhevsky Medal to Dr. Erika Palmerio. And now I call Dr. John Linker to the stage to tell us his appreciations.
Well, it was my great pleasure to nominate Erika for this award. When I think about what makes Erika such a special scientist, it's not just strong physical insight, but great breadth, versatility, and organizational skills. I first really met Erika at European Space Weather Week in 2018 when we were in Leuven. And of course, while most graduate students would just be worried about getting through their talk and everything, she organized and co-wrote the Euphoria song that was performed splendidly at the music night that night. Emilia invited me to be Erika's opponent for her defense in Helsinki. And if in the Nordic system, or what's common in a lot of Nordic universities, of course, then there's an opponent who goes through the whole dissertation and asks penetrating questions. And so, of course, I had to read all of Erika's work, and she had 5 outstanding papers. And the first thing that really struck me was how well written they were. And so, of course, she performed great at the defense. And once again, though, the real triumph was she organized this amazing party on this island off the coast of Helsinki. As you heard, she went to Berkeley with the Jack Eddy Fellowship. And so when her fellowship ended and we were looking for someone who had the opportunity to offer her a position at Predictive Science, and what was the first thing that she cared about the most? She said, I want to be a principal investigator on proposals. Of course, for an organization like us, that is just what we want to hear. And Erika has won 3 projects. She's principal investigator on 3 projects right now. And of course, at Predictive Science, she's now added CME modeling to her repertoire, and also observations and modeling of solar energetic particles. And you already heard, of course, that she's still so active in meetings. I think she's co-organized sessions this year at EGU, Shine, and IAGA, co-leading an EC team. And I also know that she's played a big role in Music Night tomorrow. Finally, what I was going to note is that a lot of people probably don't know this, but she just became a U.S. citizen. And so it's kind of ironic that she's coming back to European Space Weather Week as her first talk as a citizen, because while I think life is a lot more convenient in the U.S. if you're a citizen, I think deep in heart she's still very European. So it's my pleasure to congratulate you on this award.
Thank you.
Oh, she needs the mic. Yes,
This microphone keeps being stolen. Thanks, everybody, for this enormous honor. So I will be brief. So, of course, first body of work to thank would be the E-SWAN Medal Committee. Thank you so much for this honor. Thanks to my nominators that now have been revealed, John Linker, And obviously the support letter writers. And John, now you get a second thanks, because, well, obviously I have to thank all my mentors throughout these years. Well, my academic path has been already explained very well, but yes, so I thank Emilia Kilpua, my PhD supervisor, Christina Lee, who was my postdoc supervisor, and now John, who is my current boss and mentor. But science is not just, you know, the researcher and their mentor directly. Obviously, science is made with collaborations with as many people as possible. So a big thanks to all my collaborators throughout these years. Obviously, I can't mention everybody, otherwise we will never make it to the welcome reception, but you know who you are. And well, apart from now my closest geographically collaborators in the US, I'm also very thankful about all my collaborators in Europe, because apart from scheduling all these meetings between 5 and 6 a.m. for me, because of time zone constraints, they really keep me very tied to the European community, which, as John said, will always be my home community. Sorry. And I feel very lucky that in this field, I mean, I don't know if it's just me grabbing the best people or if it's just a field of awesome people, but like I have so many collaborators that I can call like very close friends in life, which is awesome because, you know, it's how you get to do work that is actually fun, like it doesn't really feel like work. Then obviously I have to thank my husband, who is not here today, for, well, first of all, for being a very good collaborator, like he's also in the field, if you don't know. So yeah, we get a lot of exciting science conversations at home, at the dinner table, but also for his supportive spouse role, for example, in cooking dinner when I'm too stressed. And finally, a big shout out to all the early career scientists in this field. Now, apart from, well, I have a lot of friends from the US who can't be here because of travel restrictions. So apart from the US, there is like the most, you know, clear situation right now. I mean, it's overall like the world is not a great place right now to be in general. So a big shout out to all us early career scientists for, you know, we are keeping in there and trying our best. So thanks everybody.
Thank you. Congratulations. Okay, so again, congratulations and thank you. Again, I would like to thank for all the nominators because these awards couldn't work without nominations. And I would like to thank also for the local organizers' technical support to make this ceremony possible. Also a lot of work what the awards committee did and for the support from E-SWAN. And also thank you for coming to the ceremony. And now, after a few minutes break, there will be the medal talk, the medal session given by Erika. So please wait a few seconds. Anything else? Here? Maybe. Then probably 20 plus, right? Because then I have to close and then we still make a photo.
Okay. So you want okay? I have too many earrings apart.
If it's 30 minutes now? 35 minutes.
They make noise if they
Exactly. Well, then otherwise you take this one.
Is it? Yeah.
Yeah. You're supposed to open the jacket pockets. Yes. So I think.
What now?
She can go.
You do a presentation.
Okay.
Yes.
Then I will start. I just announce, and then
Should I go now?
First,
But
no,
am I
no,
microphone?
no,
No.
That's I will call her, and then you. Okay. Everything settled?
Yeah.
Let's start. So now we will start the medal talk session, and I call immediately Mateja Dumbovic. She was the Chizhevsky Medal winner in 2020. She will be the chair.
Okay, hello. So I will give Erika 20 minutes, but if she's a couple of minutes more, we will tolerate. I will give you at 15 minutes, 5-minute warning. Everybody who wants to put their question in the official app, please, you can do that when Erika is speaking, also later. And everybody who is in the room, you can just put your hand up. I will run around the room and try to catch you. If you can, please try to move closer to me, not to wait. But yeah. So, Erika, please give your talk. I didn't know the title, so you read it.
Okay, yes. I am microphoned? Oh, yes, yeah, I can hear it. Hello again, it's still me. So yes, it has been mentioned that I work on many things, but yeah, I had to choose a topic, and I chose to talk about my dear CMEs and how we chase them from spacecraft to spacecraft. This thing vibrates every time you click. Great. So why do we care about coronal mass ejections? Well, of course, they are an integral parts of the solar eruption mechanisms. We know that they are very efficient particle accelerators from the corona to the heliosphere, and they're major drivers of space weather effects, not only at Earth, but also throughout the solar system and at the other planets. And as we all well know, at Earth, the ability of a CME to drive a geomagnetic storm will depend mostly on the direction of its magnetic fields and the speed of the CME itself. But now, how do we understand the 3D configuration of CMEs? Well, we observe them in two main regimes. So in remote sensing, we have very pretty 2D pictures. And in situ, we have 1D line plots. But clearly, in most cases, this is not enough to get a full picture of how solar eruptions are structured and how they evolve. Because obviously CMEs are huge magnetized 3D structures. So a lot of the work of observational CME researchers is to try to put out 3D complete pictures of something that is gigantic from photographs and squiggly lines. And there will be a few, and I was told that I can point straight at the... Does it? Wow, okay. There will be a few in situ plots, and by a few I mean a lot, during this talk. So they will be more or less, all structured as, at the top we will have, no, I always fail at this, okay. At the top we will have magnetic field magnitude, then magnetic field Cartesian components, angular components, speed, density, temperature, and plasma beta. More or less, they will be structured like that. I will announce if they're different. So, for example, from a 1D in situ plot, we might want to derive what the magnetic structure of a CME is. So, for example, here I've put a very, very idealized, and it's a real CME, but it's very traditional textbook one, where we can look at the directions of the latitudinal magnetic field. The one there. Oh, this one? Yes. Oh, okay. I can try that. Thank you. Give me 5 minutes, I will fail again. So here we look at the latitude, for example, from north to south, and then in the longitude we have the field pointing to the west. So from that we can deduce what overall the structure of the CME would be. And that would then form the very famous flux rope structure of CMEs, which are, what is a flux rope? It's a bundle of twisted magnetic fields that wound about a central axis. We still maybe do not agree on what happens before a CME erupts, but we pretty much all agree that all CMEs leave the sun as flux ropes. Here I've put a few sketches of like the very basic types of thank you, of the very basic types of flux ropes. So in all of these sketches, the letters under each of them would be the field, the direction of the field that a spacecraft crossing the screen would see as the CME is passing. So first we will have the front or like the outer helical fields, which point in one direction. Then we will enter the axial field and then the inner helical field. So one would say, okay, we have these basic types that we can look at the magnetic field and derive. We have in situ measurements, so that's it, right? Well, no, things are not that simple because CMEs do not propagate unchanged after they erupt because they are not propagating through vacuum. So we have interactions with the ambient medium, which would be the solar wind, but also other transients. So, for example, other CMEs or stream interaction regions, and that can lead to deflections and rotations of the structure as a whole. And obviously, that has very crucial implications for space weather forecasting. But also, we know that CMEs are not really solid bodies, so we expect to see local distortions and even multiple orientations within a single CME, depending on where you cross it. So that's even more challenging for space weather forecasts. So we really have to improve our intrinsic understanding of how CMEs are structured and evolve to improve then our forecasts. So one great way to better understand CME structure is to take advantage of multi-point observations, because in remote sensing, we can get a better characterization of the overall geometry and propagation direction. And for example, we can solve the very basic problem of near side, far side ambiguity. And in situ, we can try to piece together the overall structure of a CME from 2 or more, hopefully more, 1D cuts through it. But also, we have to keep in mind that in situ observations are also not really easy to interpret, because whilst, for example, in remote sensing, we're looking at simultaneous images in time from different viewpoints, when we encounter a CME in situ, since we don't have a dedicated constellation, so we only rely on very propitious encounters, we have CMEs that have evolved from one spacecraft to the other. So not only we are looking at structural differences, but also at evolution at the same time. So for now, I decided, from now on, I've decided to show a few examples of multi-point observations of CMEs and what we learned. And I've decided to divide it into the 2 solar cycles that I've been operated during, which are 24 and 25. So during solar cycle 24, in terms of heliophysics dedicated space missions, we had, near Earth assets, of course, plus the twin stereos. So stereo was really revolutionary in terms of multi-point remote sensing imagery, because those were the very first pictures away from the Sun-Earth line. And we had 2 heliospheric imagers looking at the space between the Sun and Earth at all times. But in terms of in situ measurements, because of the orbit, so the 2 stereos were drifting away from Earth, like this, in time, just because of the orbital configuration, the chance of catching the same CME with 2 or more of them became lower and lower as time went on. And the stereos were launched during solar minimum, so we had very few events to look at. On the other hand, solar cycle 24 had a considerable wealth of planetary missions through the heliosphere. So, of course, we had to take advantage of them to chase CMEs. And despite the limitations in terms of data availability, because, those were planetary missions, so they might not have all the instruments that we CME people look at. So, for example, they might be missing a magnetometer or a plasma instrument. But also, obviously, planetary orbiters are orbiting a planet. So they are many times, most of their orbit is inside the magnetic environment of a planet. So we normally look at just a tiny bit of portion of a spacecraft orbit that is in the solar wind. But also sometimes we had to really get creative and try to understand how a CME was propagating, how large it was by looking at the effect of the CME on the planet. Let's go back 1 second. So we're going to look first at this event that I have here. This is the configuration that would have been for this event without planetary missions, so without using planetary missions. So we would have had Earth and the two stereos. But by adding planetary missions plus a bonus astrophysics mission, we had a much bigger coverage of the inner heliosphere. So now we can look in more detail at this event. So this was a CME eruption from 2012, May 11. And in remote sensing, it was well observed by the usual suspects, so Earth-based assets and then the two stereos. And here there is a quick look at WSA and simulation that estimated impacts of this CME at Earth, Venus, the Spitzer Space Telescope, Mars Science Laboratory, which was en route to Mars, and that's, for those who don't know, that's basically the Curiosity rover, and then Mars itself. So then we want to look at data from all of these assets to see, okay, where is the CME? So we found, we're not going through all of these plots, obviously. So the expected in situ observers all detected CME signatures, excluding Spitzer, because obviously that's definitely not even a planetary mission. But all of them, so including Spitzer, registered an almost simultaneous solar energetic particle event with a very strong impulsive profile. That was related to the ground level enhancement number 71 at Earth. And so for example, at the Spitzer Space Telescope, if you're curious, what happened was that we looked at the number of saturated pixels in the infrared camera, and the number of saturated pixels normally goes up and down with the solar cycle because of cosmic rays, but when there is a big SEP event, we have more saturated pixels in the camera. Also for Mars, that was before the launch of MAVEN, so we didn't have magnetic field information, but to find the extent of the CME as it passed Mars. We also got quite innovative and looked at the altitude of the Mars hybrid magnetosphere boundary, how it was being compressed, and then it relaxed after the CME passage. But so we found all of these SCP signatures in all of these spacecraft, so we looked at everything else that we had available, so we also added the two stereos and Mercury. And the point is that all of these particle observations revealed that the 5 original ones also this impulsive profile because of the passage of the CME. So these particles propagated very quickly inside the CME, whilst all the other observers had a much lower rising profile. So even if we were indirectly deducing all of these things, the conclusion was that all of this multi-spacecraft analysis was very useful to infer the all CME extent through space. Another event, so here we looked at two beautiful filament eruptions. We can see, again, the usual suspects. Yes, they erupted in close succession from nearby source region. They were both roughly Earth directed, and this time on the path we had Venus, Earth, and then Saturn. So now imagine that we had to find something from 1 AU. So from Venus to Earth was fine. But then we had to follow this thing from 1 AU to 10 AU with nothing in between. So yeah, it took a while. But yes, we found signatures of the structure at all 3 planets. So yeah, we did find a flux drop structure at all 3 planets. We found clear interaction signatures at Earth from the plasma. So we have the CME eject extent is the one shaded in green. At Venus, we have, unfortunately, a data gap right in between, so we couldn't see if there were interaction signatures as at Earth. But then, yeah, at Saturn, we saw a much more complex and distorted magnetic configuration. I'm doing terribly with microphone and pointer. Through some plots, you will see these pink lines over magnetic field. These are flux drop fitting, so we are fitting with a flux drop model the measurements to recover the orientation of the CME itself. So what happened after we looked at all of these observations, while we tried to map them between each other. So here there are some examples of different structures that we mapped. Here in the bigger panel we have the full ejecta. So we were taking expansion from one location to the next into account, and then we normalized all the observations. And obviously it's hard to read the plot, but I will say that green is Venus, blue is Earth, and red is Saturn. So we can see that the blue and gray line, which are Earth and Venus, follow each other very, very closely. So clearly Venus and Earth are observing exactly the same structure, but we have some deviations at Saturn. So it was still unclear whether the structure corresponded entirely to these two CMEs that have evolved simply, or if interactions between 1 and 10 AU with the solar wind led to a merged interaction region. So obviously having more spacecraft on the way would have been much more exciting, but we tried what we could. I was told not to move my head. And now the last event for Solar Cycle 24. So now here we are in 2018. So we have already lost stereo B, so we have remote sensing data only from Earth and stereo A. Here it was two very faint. This event has also been described as stealthy. I mean, it's not really stealthy when it erupts, but its effects at Earth were definitely unpredicted. So in here we estimated these two CMEs to interact very more or less in the outer corona. And then to arrive at Earth and Mars as more or less merged or merging structures, since Earth and Mars were almost aligned. So here we tried, well, it was after the launch of MAVEN, so we had magnetic field measurements on Mars. So we tried to really work on comparative space weather, meaning that we tried to get exactly the same or similar data sets for both planets. So again, okay, now the lines are blue and not pink, but the lines of our magnetic field are flux drop fits. So what we observed at Earth is the first of the CMEs in pink. So here I just splitted the same plot into two panels because it was very tall. So the first CME, we have it in pink, and we have a shock from the second CME inside the first. So we are catching these two CMEs at the beginning of their interaction. And then for the second actually drove the third strongest geomagnetic storm of Solar Cycle 24, which you wouldn't have said from how wimpy the eruption was at the sun. But then what happened at Mars was that we saw the first CME in a very, very, very similar status as we saw it at Earth. So as if almost it hadn't, like, apart from expansion, there wasn't much evolution going on. But then we basically almost completely missed any signature of the second one, which was the one that drove this enormous geomagnetic storm well, not enormous, major-ish geomagnetic storm at Earth. And that was because there was interaction with the SIR that was following the CME at Earth. Here we have the solar wind speed. So the fast wind that was following the CME at Earth had basically merged or deflected away the second CME from Mars. Now, what happened during Solar Cycle 25? So we saw and we are still seeing the operation of Parker Solar Probe and Solar Orbiters, which are the first dedicated heliophysics missions to get inside 1 AU since the 70s with Helios. Well, I guess we all know these two missions very well. And these two spacecraft have opened really a new era of multi-point measurements in heliophysics in both regimes, remote sensing and in situ. And they're really changing our understanding of how CMEs are evolving and are structured in the corona and in the heliosphere. First of all, now we have data that are really heliophysics dedicated data. So we have magnetic field and plasma for most of these events. So here we're going to look at the CME eruption on 2021, September 23. That we estimated to impact Bepicolombo, Solar Orbiter, Parker Solar Probe, and Stereo A. And they were more or less equally spaced in radial distance, 0.4, 0.6, 0.8, and 1 AU. So it was, and they were almost fully radially aligned. So it was a really cool investigation. So here are the four sets of measurements. At Bepi Colombo, we don't have plasma. So it was a pretty weak event observed at all 4 locations. But what was striking is that the top panel, the magnetic field magnitude profile, was very different between the 4 in both the sheaths and the ejecta. But the overall rotation of the magnetic field was roughly comparable across the 2 observers. And also we had way clearer CME ejecta boundaries at 2 locations and way more complicated boundaries to define at the other 2. Here it's again a spacecraft mapping, so we are mapping and stretching and normalizing all the 4 sets of measurements. So we have an overall agreement at the global level, but we can find some prominent differences. Most of the magnetic field differences seems to be in the BR component, which is the radial magnetic field, here the second panel, which then reflects into the magnetic field magnitude. And that's also very interesting because, for example, the shapes, the characteristic shapes of these curves suggest a more central encounter at Solar Orbiter and Parker Solar Probe than at Bepi Colombo and Stereo A, but we know that Parker Solar Probe and Stereo A were the 2 probes that were the most radially aligned. So we are clearly missing some pieces in how CMEs really evolve in time, because here we're looking mostly at evolution in time, since we are mostly separated in radial distance. Then, okay, this study was actually mentioned earlier. Maybe we can make it, yeah, a couple minutes. So this was an impressive filament on 2022, February 15, from the far side. Actually, in solar cycle 25, all the best events are happening from the far side. I don't know why, but yeah. At that time, that was the most distant filament seen in EUV by Solar Orbiter EUI, so super cool. We have it here. And this was a pretty fast CME in the corona. And also here we have some images of Parker Solar Probe WISPER, so the inner telescope. And Parker Solar Probe has really changed our understanding of CMEs and their early evolution, because we have started to cross CMEs as they are, image CMEs as we are crossing. So we are flying through them as we image them, which is very cool, but also very complicated to interpret. So here the orbits of the planets are gone, but we are at Mercury's orbit with Parker Solar Probe and Bepi Colombo, more or less 0.35 AU. So here we are not that close to the corona, but for example, between the second and the third frame, that's where the shock hit Parker Solar Probe. So in the last frame of WISPER, like Parker Solar Probe is already measuring the CME as we're seeing it, which is quite cool. But now we had these 2 spacecraft very close to each other. It was very less than 5 degrees in total angular separation, so both latitude and longitude. But we can see that, well, yes, overall it might look like the same CME, but we have very different measurements between the 2. And at Parker Solar Probe, for example, we couldn't even define a single magnetic structure. So we divided in these 2 different grade areas, the core of the flux rope, which we call the magnetic cloud, and then a more elongated magnetic structure that we call the magnetic obstacle. And we didn't have this distinction at Bepi Colombo, which was extremely close. Obviously, this was a very intense, detailed study of mesoscale structure of CMEs. But for example, here is just an example, we tried to look at how the magnetic fields are correlated between Bepi Colombo and then the 2 different structures that we identified in Parker Solar Probe. And we couldn't even find which one of the 2 would match better Bepi Colombo, because for the magnetic cloud, we found a moderate correlation in the B magnitude and moderate to strong in VT, but then in the other 2, not great. While for the magnetic obstacle, we found very moderate to strong correlation for all the components, but almost no correlation for the magnitude. At last, so almost done, Matteo. This is another extreme event, again hidden from view because they all happen from the far side. So here it was an eruption on 2023, March 13, but nobody saw it happen. So we have some off-limb observations from our imagers, but we don't have a visual of this of the eruption source and structure. And we have an in situ impact of the ejecta only at Parker Solar Probe, which was at more or less 0.25 AU. And this was one of the fastest shocks ever recorded in situ. I mean, you can see the CME in the coronagraphs. It's pretty spectacular. What was super cool about this event was the configuration of heliospheric imagers. So we had solar orbiter and stereo A looking at opposite sides of the sun, so creating almost a punch-like view before the launch of Punch. And we can really see this global shock that we can see going all circumsolar around the sun. And another big novelty from Solo High, the imagers on Solar Orbiter, is that for here we are not that close to the sun. We are at about 0.6 AU, I think. But we can already, well, obviously now it's not a very detailed movie that you see here, but we can really see the fine structure of CMEs in the heliosphere at a much higher resolution than the stereos. The previous generation. And again, here with Parker Solar Probe, we are flying straight through the CME. And here we're trying to map Solo High and Parker Solar Probe. And this is still work in progress, this very last event. So what we are trying to do is try to, first of all, map what is going on between all these heliospheric imagers, but also trying to contextualize the Parker Solar Probe in situ measurements, which are the only ones that we have. Please don't look at the plasma data, because we are the team, this CME was so fast that it kind of saturated all of the plasma instruments. The teams are still working on processing much better all this data. The in situ observations at Parker suggest a flank encounter from how they are going, how the magnetic field components are behaving, for example, the large BR component, but we couldn't even define the associated endedness of the CME itself with flux drop fitting techniques, because as you can see, trying the two different endednesses gives very similar results. And we don't have a view of the source of the eruption. So this shows that even if we have more observations, they become more and more complicated, and it's really complicated to try to figure out what's going on with CMEs. So to conclude, we still have many questions, as I said. More questions are being formed as our observations get better and better. So I'm waiting for the new challenges and discoveries from Solar Cycle 26. Thank you.
Okay, thanks, Erika, for the great talk. Are there any questions? Currently, we have none online, some in the room. While we wait people to get the courage to ask the question, so maybe a question from me. So we have quite some examples now of events where we have either nicely aligned spacecraft or close to each other, but showing totally different CME signatures.
Yes.
So what's up with that?
Well, as I said, so I think that to figure out better what's going on, obviously, well, I had to choose a topic, right? We can talk about everything, but at the moment, I think that one good avenue to look at is complement of these observations with MHD modeling. And when you try to model something to reproduce an event and not to forecast, so you can tweak things, it becomes much harder when you have to match 4 or 5 observers in the heliosphere. So what goes wrong in the modeling can actually be used to explain what the data, and what you get right, then you can use the models, because when you are obviously modeling something, you have a full 3D cube. So you can then look at the parts that are not covered by real spacecraft and see what's going on there. So yeah, it's a lot of work in progress, but we're doing our best.
This kind of stuff is explainable with MHD models, right?
Well, not all the time, because, well, with MHD, we're obviously ignoring most of the time stuff like turbulence, because, the domains are so vast that you have to make a choice on your scales, right? So probably we will have at some point to complement global MHD modeling with smaller scale MHD modeling to get the smaller scale structures like turbulence structures, mini flux ropes, and islands. But yes.
There was Chris. Okay.
Oh, congrats.
Thank you.
What is your dream type of mission? What data would you like to work on next?
Okay, what's my budget? Infinite budget?
Unlimited.
Oh my God, this is the dream. Okay, first of all, I need a spacecraft at the L1 point of every single planet, okay? First of all. Second of all, I want a helio cube, like a grid that moves as a cube, you know, whatever you want it, but so that we can catch the same CME, for example, with 100 CubeSats, yes. With like 100 CubeSats in a grid. Because it's very important that we have something in a lattice/grid formation so that we can look at, first of all, measure the same CME at the same time, and we can look at differences in latitude and longitude at the same time, and then with the same kind of slices of observations at different radial distances, we can look at the evolution. So yes, but I think that my budget would be very, very high, so yeah.
Okay, I think Stefan and then Volker.
Thank you, Erika, for the nice talk. When you overlay these measurements with these magenta lines, you say you use this flux tube fitting. What kind of flux tube model do you use? Because let's be honest, this is a mathematically ill-posed problem, right? If you just have one satellite going through the
So CME, you mean like basic flux tube fitting?
Right, so we can use different, you can explain the same observation with different flux tube models.
Yes.
So which one do you use and how do you do that with bringing the parameters?
So there are a lot of different kind of models, right? We have the very simple ones that are just a cylinder. We have the cylinder that allows for expansion, which is the one that I mostly use. But then there are models that have much more distortion involved in them. Now, the problem is that the more complex flux model we get, the more free parameters we have. So the more free parameters we have, the more the solution will be degenerate. So that's why I try to go first with the simplest one. If this kind of simplest models give you a reasonable answer, then we can go with the more complex ones. But yeah, not even sometimes, like many times, like all flux rope fittings give terrible results. And that just tells us that CMEs really distort and feature like local disturbances that we are not accounting for in the very simplified models.
But also you are using Lundquist type, right?
Yes. With expansion, yes.
Okay, Volker?
Yeah, congratulations, of course.
Thank you.
And then I was very impressed by the presentation. The aspect I found very fascinating in my own view was to see in these multi-spacecraft observations that the overall north-south or rotation is a global thing, whereas the fine-scale variations are more locally and so on. You see this the same way, similar way, even in the ground magnetometer data for magnetic cloud type inputs. You have the overall driver, the solar wind driver, but on top of this you have small scale variation which are likely related to internal magnetospheric processes. So I saw this very nicely.
But that's mostly because I try to look at radial alignment as much as possible, but I assume that the more we get far from each other measurements in terms of longitude, the more the rotation might not be preserved. But yes, it's promising that at least when we're looking at more or less the same radial direction, we are finding globally that things tend to agree with each other, which is promising.
Okay, I was told that I have to end this discussion because we have to go for the welcome reception.
Yes.
So let's thank and congratulate Erika again.
Thank you.